So previous class I have discussed, we will stop from here. So before it starts that one component systems and two component systems, it is very important to start one equations, that is classes clapping equations. So topic is classes clapping equations. What that equation says? This equation says delta P by delta T equal to delta H by T delta B. This is the classes Clapeyron equations. What is delta H here? This is heat of phase transformations. And what here that B, delta B is B2 minus B1, and what that B says that molar volume of pure substances pure substances at let's say for B2 at pH 2, and for B1 that is molar volume of pure substances at pH 1. Okay, so here dP is change in pressure and dt is change in temperature, and that T is temperature. Okay, so what these equations is used in phase transitions. So these equations dP by dt equal to delta H T delta B is used in phase transition. These equations. So how it is used? Let's say for case 1, let's say case 1, if the change is between liquid to solids or solid to liquids, let's say solids to liquid or liquid to solids. In this case, the change in pressure is negligible. So if change in pressure is negligible, then the delta B is constant, and if temperature is given, then the equations, that is classes Clapeyron equations, is become dP by dt delta H T, this temperature is given to you, by delta B, and this delta B is constant. Okay, T is given and delta B is constant. So these equations we will use for this case. And suppose if temperature is not given, or different temperatures are given, or different temperature is given, on that case, what you do? That Clapeyron's equation says that dP by dt equal to delta H T. This T is not given to you, and then what you say that we will do the integrations. Okay, so what the integration says that what you do, that dP by dt equal to delta H by delta B, because this delta B is constant and delta H is also constant and T is not given, means that is not constant, and 1 by T. So what I do, I will take T here to integration. So this is delta H by delta V, that is dt by T. So if we do the both side integrations, if I am doing both side integration, that is become delta P, that is delta H by delta P. So this will become ln T2 by T1. So this is the equations if temperature is not given, if different temperatures is given, like T1 and T2. And for case 2, if you take that case 2, then case 2 is for solid to gas, or gas to solids, or liquid to gas, or gas to liquids. On that case, the Clausius-Clapeyron equations is, that is dP by dt equal to delta H T delta V. So in this case, for solid to gas and gas to solid and liquid to gas and gas to liquid, in this transformations, in this transition, the pressure will not be negligible, So this delta V is not constant. So if delta V is not constant, then what you do, we have to take that approximations. So for this case, we have to take approximations. What one approximations we will take that this liquids volume of liquid is very high compared to volume of gas, because gas occupied, wherever you keep the gas, that gas occupy the whole volume of that area. So that volume of gas area is very high compared to volume of either liquids or gas. So volume of gas is much more than volume of liquid. So what you say, that volume of gas minus volume of liquid nearly equal to volume of gas. Similarly, volume of gas is much more than volume of solid. So volume of gas minus volume of solid is nearly equal to volume of gas. This one approximations we assume, and another approximation we take that this gas is taken to be ideal gas. So these two approximations we will take and derive this Clausius-Clapeyron equations. That means here dP by dt equal to delta H T, and this B is volume of gas minus volume of liquid, or this may be solid. And what I say, that this is nearly equal to volume of gas minus volume of liquid or solid, nearly equal to volume of gas. So what, like delta H by T volume of gas, and we assume that gas is assumed to be ideal gas. So Lord, I write dP by dt. So ideal gas means PV by nRT, right? So P is equal to nRT by P. So in place of B gas, I will take this value. So I will put here dP by dt equal to delta H T. Then I will take nRT by P. So this will become dP by dt, that is equal to delta H nRT square, and P will go above, then P delta H. So if you do the integrations, if we do the integration, then what happened? dp by dt p delta h nr t square. Okay, so what I do, I will take p here, so dp by p I will take here and t I will take there, then delta h and n constants, r constant because n is number of moles, r constant, gas constant, and delta h is constant. Okay, then that will be t I will take here, dt by t square. So this will become dp by p, and I write delta h by nr, this t I can write minus 2 dt. Okay, and because we know that n minus x, this is equal to minus of n minus x, sorry guys, oh my god, this is minus n x plus 1. Okay, this is the value. So here n minus 2 is going to give how much? So this will be that is minus x plus 1 with n, and here again is minus x plus 1. This is that, then this is what, minus n. So x is here minus 2, so minus 2 plus 1 is how much? Minus 1, and into whatever that n, so into n, and again this is minus x is minus 2 plus 1, that is minus 1. Okay, this is the integration rule. So you apply this here, then dp by dt, that is equal to delta h nr, so this minus, so minus delta h nr, and this value minus 2 plus 1 is minus 1, and this n is here t, and this is minus 1. Okay, so where x equal to minus 2 and n equal to t. So if you do that, then you will get this. So dp by dt, this is equal to minus delta h nr, this is 1 by t. Let's say from t1 to t2, then this is going to be dp by dt, this is going to give so this is dp by p, right? Sorry, dp by p, dp by p, dp by p equal to this value, this is, so dp by p is ln, let's say p1 to p2, then ln p2 by p1, that is equal to minus delta h nr, so this is 1 minus t2 by 1 minus t1. So this is the value if the solid to gas or liquid to gas or gas to solid, liquid to gas transformation is happening. Then by using that Clausius-Clapeyron equations, now we can get the values that ln p2 by p1 equal to minus delta h n r 1 by t2 and 1 by t1. So how you use these Clapeyron equations in our page transitions? Let's say, so we already discussed that components, what is the page, and how to find the degrees of freedom. So let's say water, solid, form, and this is in page transformations to water of liquids. Then what are the total number of pages here? So page is 2, so solid, another is liquids, and so components is S minus R. S means in the species which exist in independently. So two species are there which exist independently. So 2, so that is 2, and one condition. These conditions comes from this equilibrium. Then 1, that is components is 1, and F equal to C minus P plus 2. So component is 1 and pressure is, the page is 2 plus 2, so page is 1. Okay, so components 1 and page is 2 here. So the degrees of freedom means, that is degree of freedom for formula C minus P plus 2. So here that components is 1 and here page is 2, but if we say that minimum number of pages required to exist the system is 1, because if we say that if page is 0, then if page is 0, then 0 plus 2, then it will come some as 3 pages, but I need that minimum, like, so that system is exist. So for system exist, so minimum number of page required to exist the system is page equal to 1. Here page equal to 2, but the minimum numbers, so that the system is exist is 1. Okay, so either for one component, two component system, so minimum number of page required to exist a system is 1. Okay, so F is, so for minimum degrees of freedom to exist a system is, that is C minus P plus 2, and for minimum this is 2 here, so page is 1 here, so 1, and for minimum means 1 page is needed, this one plus 2, so this is component is 2. Okay, so here the page is 2 for explaining that one component system. Here the page is 2 pages are available here, but I think that we take that minimum, so that it will be like I can easily explain that any state of that of a components that we will discuss while we proceed this chapter. So minimum page, that is one I needed, either it's from one components or for two components to explain the system. So that is 1, so 1 minus 1, that is 2. So here degrees of freedom is 2, means 2 variables are needed. F means variables, so 2 variables are needed to explain a point. Okay, so these 2 variables may be pressure, temperature, or maybe composition, temperature, or maybe composition and pressure. So any 2 variables. So here we will take in generally pressure and temperature, or one component systems. So for one component systems, if I am taking pressure and temperature as the variables, then what I says that pressure by temperature, and we know that the slope is that y-axis divided by x-axis, so slope is y2 minus y1 x2 minus x1. So in y, that is p is there, so p2 minus p1 and t2 minus t1. This is the slope equal to tan theta. This is the slope, so p2 minus p1, t2 minus t1, that is dp by dt. And we want to know that whether this slope is whether positive or negative, and because we have to put this or we have to put like this. So this is positive slope, this is negative slope. So how you understand that? What is the slope? Actually we want to explain a point in one component systems. So for explaining a one component system, we need two variables, let's say pressure and temperature. And suppose one point is here, so we want to explain this one, so we need two components, pressure and temperature. For that we need a slope, so that slope is whether positive or negative. So that is given by the Clapeyron equations. What it says that slope is dp by dt, and this value is delta h t delta b. This is given by Clapeyron equations. And what the Clapeyron equation says that dp by dt equal to delta h t, and this b is, let's say, b of liquid minus b of solid. And if b of liquids is greater than b of solids, then what this value is going to come, b of liquid minus b of solid is positive. And if this is positive and this value delta h is positive value, then dp by dt, this delta h is positive and this value also, temperature is always positive because we take in Kelvin, so temperature is always positive, so this is positive, then this is positive, so this is equal to positive value. Okay, delta h value is positive, so here we take delta h value is always positive. So if this is positive and this is positive, then dp by dt is positive, and this represents the slope because we take this graphs, pressure by temperature, and slope's value is y2 minus y1 divided by x2 minus x1. This is the slope. So this slope, if volume of liquid is greater than volume of solids, then this value is going to be positive value, so this slope is positive. And these are examples of, let's say, carbon dioxide and sulfurs. All this gives this delta this slope as positive. Okay, so what says, if dp by dt is this value, and if volume of liquid is greater than volume of solids, then this value is positive. So this value will come how? Like if you increasing the pressure, delta p means p2 minus p1 and dt means t2 minus t1. So this positive value how we will get? We will get either pressure p2 is more than p1 and t2 is more than t1, then this value will be positive and this value also positive, then total is positive. So he says that if you increase the pressure, then if you increase the pressure and also you have to increase the temperature, then we get the positive slope value. So in this case we have to increase both pressure and temperature. On the other case, let's say if volume of liquids is less than volume of solids, so dp by dt is delta H T B liquid minus B solids. Then if volume of liquids if volume of solid is greater than volume of liquids, then what, this value is greater, then this value is going to get negative. So dp by dt is going to get, this value is positive, so positive, and but this value is negative, then this whole value is going to get negative. It means dp by dt is slope, it means slope is negative. So and this slope in negative is come from whenever you are taking that ice, etc. Okay, so it means dp by dt is negative. It means what it says, that P2 minus P1 or T2 minus T1, and we want this value is negative. So for that case we need that this value is negative. On that case what, P1 is greater than P2, so that this will get negative value, and another one, the T2 has to be greater than T1, so that here you get positive value. So that negative by positive equal to negative value. Okay, so what it says, that if you increase the pressure, then if you increase the pressure at the same time we increase the temperature, then we get the negative slope. Or if you decrease the pressure and increase the temperature, then we get the negative slope. So this we obtain by doing this. So this is done in case of ice, where slope is negative. Okay. And this value, this is done for like carbon dioxide and sulfurs, where the volume of liquid is greater than volume of solids, so that this value if you put, then this will going to get positive value. And this Clausius-Clapeyron equation says that where is that equation? Says Clausius-Clapeyron equation says that delta H T be liquid and B by solids, and if this value is positive, then this is positive, then this positive by positive get the positive. So slope is positive, because dp by dt represent the slope, because here y-axis is taken as p and x-axis is taken as t. So slope is y2 minus y1 divided by x2 minus x1, that is the slope. Okay, so that is the applications of Clausius-Clapeyron equations here. So let's discuss that one component systems of and two component systems one by one. Let's say we discuss about of that water. So this is one component systems. One component system. Okay, so first example is, let's say take water. So here we discuss that slope is negative, that is dp by dt is negative value. Okay, so I will get, if you put that pressure and if you put the temperature, so dp by dt is negative, means negative slope is like this. So this is negative slope, and what is with it here, like this, or let me draw the picture good. Okay, this is the negative slopes. So what I do here, okay, so what is that, okay, So this below area represent as SB, or this below area is represented as vapor, and this above area, this area is represent the liquids, and this area, this left side area is represent the what? Solids, because water exists in three forms, that is three phase. One is liquid phase, another is vapor phase, another is solid phase. So I represent this three phases and three areas. So now what you discuss is actually here three things you will discuss. One is carbs, and secondly you will discuss that areas, and third you will discuss that the point. So at carbs, what is that equilibrium conditions at carbs, and what is at carbs what it explains, at areas what it explains, at points what it explains, that we will discuss in one components and two component systems. So here let's say I give the name, let's say this value is O, and let's say this value is A, let's say I value this B, and let's say this value is C. Okay, so now what is the carbs? Let's say I explain first carbs. Carb AO, what this carb AO explains. So in this carb, above side, so this carb AO, above side is solid, below side is vapor. So in this carb, this solid and vapor is in equilibrium. So carb AO explain that solid and vapor are in equilibrium. Okay, similarly if I write carb BO, so what they explain that above side liquid, vapor, below side vapor, so this is liquid and vapor are in equilibrium. Similarly carb for CO, what it explain that one side is solid, other side is liquid, so that is solid and liquids are in equilibrium. Okay, so this is the classic AO. AO means this and this, and BO means this and this, and CO means this and this are in the equilibrium. Okay, so first points we will discuss about of the carbs. Next we will discuss areas. So areas, area is this area. Okay, so this area, this area, this and this is one area, this below side is one area. Okay, this below side is one area, and similarly COB means this area, and COA means this area. So what the area of AOB says? Area AOB. So in this area AOB only vapor is there. So here only we found vapor. Okay, and what about the area COB? Only liquid you will find in this area. So area COB only liquid. Similarly in the area of COA only solid. Okay, area COA only solid. Okay, and third point we will discuss about of the point. Third we will discuss on about point. So point is only O. This is not, this point we will not discuss. This is one, the triple point. means this curve also meets here, this curve also meets here, this curve also meets here. So triple point, not point. I will write that triple point. Triple points, sorry. Triple point. So the triple point here is O. So at O, what we are find at O, what things we get, that is solid is also here, this one here solids, and here liquids, and here vapor. So in point O, that is solids is equilibrium with the liquid is equilibrium with vapor. So three things we will find: solid, liquid, and vapor. Okay. So after that, what we says that, so why you are searching these curves, why you are searching this area, why you are searching triple point? Because you want to explain. Suppose one point is here, let's say this M point is there, then what I want to explain this point where this M is located. So we are going to explain this point, then what things we needed. That's why we are studying this liquid and this and diagrams like P by T plots. So what is here, the solids and vapor. So what are the pages, and in these things, so here how many pages are there? So 2 pages. Solid is 1 page, vapor is another page, so page is 2. And how many components is there? So since we are studying one component, so component is 1, although also you can find component means S minus R. So S is individual species which exist individually, so 2 species, that is 2, and 1 equilibrium condition. R means condition, equilibrium condition minus 1, so page is equal to 1. And degrees of freedom means C minus P plus 2. So C is 1, P is 2 plus 2, that is equal to 1. So F is 1. So any points, what the F equal to 1, what does it mean? Say that for explaining any points, if it is present on the curve AO, only one variables we need. Either it may be AO curve, either it may be curve BO, either it may be curve CO. If the points, let's say one point is there, let's say this N, let's say the point N is there on curve BO. So to explain this point N, we need one variable. Okay, so that's what it says, that if the F equal to 1 means how many variables are needed to explain this point. So we only need one variables because it already in this point. So because this point is already in the curve, so here only one variable is needed. So if you got this one, then we already know that this will be here. So only one variable is needed to explain if a point is, if any point is present on curve, because this is in curve. So we can already match this. Okay, so again we will do it here. So to explain any point, if that is present on curve, then only one variable is needed. If one variable we get, then other variable we definitely will get, because that point is on the curve. Okay. Similarly, if any value is present in area, like in this place, then like this M is present here, then how many variables are needed? So here it is present means we don't know anything about of it. So I think 2 variables are needed. Let's find it. So here page is 1 because only one page. Let's say for area AOB, I'm actually calculating. So in this case page is 1 because only vapor is present, and components is 1. Okay, because no equilibrium is there, so although you are studying one component, means component has to be one, or if you want to calculate, then C equal to S minus R. Since no equilibrium is there, so this condition is cancelled. So C equal to S. So species is one species, so component is one, and degree of the freedom means C minus P plus 2. So C is 1, P is 1, so C is 1, P is 1 plus 2, so this is cancelled. So okay, so F equal to means two variables are needed. F means variables, so two variables are needed to explain any points which is present in the area. Means if this is present, then we need one variable which corresponds to pressure, another variable which corresponds to this temperature, so that this M point is present. Suppose this is 8 atm and suppose this is 40 degree, let's say 300 Kelvin, then we say that this point is M is at 8 atm and 300 Kelvin. So if any variable, any like object is present on in area, then we need two variables to explain the point. Okay, that what it means is that F is equal to 2. And if any point is present is at O, then how many variables are needed to explain that points? So here how many pages are there? So page equal to 3, and components is 1 because we are studying one component systems, and if you want to find, then also you will get 1 because how many pages? Species 2, 3 species, and conditions 2 equilibrium is there, so R equal to is equal to 1, so C equal to 1, and F is C minus P plus 2, so C is how much? 1, and P is minus 3 plus 2, so this is equal to minus 2 plus 2, that is equals to 0. So F is 0. It means that if the any point, if any object is present at the triple point O, then this value is fixed. We not need any variables. Okay, since variable is 0, means we not need any variables to explain if any object is present. Sorry for the interruptions. So to explain any points, let me see whether recording is good or not. Okay. to explain that if that so if the point is present on area, then we need two triple points, and if it is present on, so what it says that if point is present at curves, then what f equal to, if triple point is present on curve, then f equal to 1. So one variable is needed, and at areas it's present, then f equal to 2, then we need two variables, and if that is present on points, that is triple points is present, then f equal to 0. It means no variable is needed. So what is say that f equal to 1, then this is called monovariant, and if f equal to 2 means one variable needed, that's the monovariant. And f equal to 2, then we need two variables, then that is called divariant. And if f equal to 0 for triple points, then the 0 variables needed, that is called mono, di, and that may forward, that may be non-variant. Yes, non-variant means no variant is needed. Okay, so this is the case for water. So here the slope is negative. So let's take if slope is positive. Let's take the case where dp by dt, that is slope is positive, like for CO2 and sulfur here. Okay, so you understand that dp by dt means how this is going to positive. We already discussed dp by dt is delta H T delta liquid minus B liquid minus B solids. So we discussed that this B of liquid is greater than B solids, and that is example of CO2 and sulfur. Okay, so here that slope is comes to be positive. Okay, so let's discuss about of that positive slope, that is carbon dioxide. So what this carbon dioxide also exists in three forms: solids, liquids, and gases. Okay, so slope is positive, so here pressure and temperature, so slope is positive. So positive slope means like this is negative slope. Positive slope means like this. Okay, let me draw good manner. Positive slope means I like to draw like this. Okay, so now I have to do like this, like this. Oh, I have drawn little beautiful picture. This is the positive slope, means this is positive slope, this is, see, this is positive slope, and if it comes from like this, then this is negative slope. This is positive slope. Okay, so here now what I will do, that I will do like this, and I will like to like this. Okay, so this below area is vapor area, and this is solid area, and this is liquid area. Okay, so similar as like we explained about of that water, similar things, just the slope is changes. Here slope is negative, so we take like this, here we take like this. Other than everything is same. So here also we will discuss three things, that is curves, and another is areas, and there is triple points. same things we will also discuss here. So if I say that, let me give the name. If I say that this, I take A, this triple point is, let's say O, this is of B, let's say C. So if I say that carp AO, so AO carp is what? Above side liquid, below side liquid. So solids and vapor is in equilibrium. Similarly, carp BO or OB, then what? Below side vapor and above side liquid. So liquids and vapor are equilibrium. As same explanation as we explained with water, only the slope is there negative, here is positive. And carp CO, this CO, so one side solid and other side liquid, so they are in equilibrium. So solids and liquids are equilibrium. Okay. So similarly here, if you calculate that page is, 2 pages are there, everywhere 2 pages are there. Okay. And with components is, since we are discussing about one component, so component is 1, also we can calculate. And degrees of freedom is C minus P plus 2. So C is 1, P is minus 2 plus 2, that is equal to 1. So same case, like we discussed about of water, same things will cut. So one variable is needed. And similarly, if he says that area, so if I says area of AOB, area of AOB means AOB area, so this area, only vapor is there, so I will put vapor. Similarly, area of COB, only liquid is there. Okay, area of COB, only liquid is there. Similarly, area of this COA, only solid is there. So here if we discuss that page is only vapor is there, so page 1, and components is equal to S, because no condition is there, no equilibrium there, so page equal to species, that is substituents, that is S. So here only 1 is there, so the component is 1. Also studying one component means component has to be 1. And F equal to C minus P plus 2. So this is 1, this is 1, 2, so this is equal to 2. So we need 2 variables to explain the points which is present in area. Similarly, triple point O is there. So on triple point O, these points, here solid, here liquids, here gases. So 3 things is in the equilibrium. So solids, equilibrium with liquids, equilibrium with vapor. So here page is 3, components is 1. So variables needed is C minus P plus 2, that is C is 1, this is 3 plus 2, that is equal to minus 2 plus 2, that is equal to C. So F equal to again 0 here. Okay. So similarly, we can explain the same way as we explain the water. So if I says that any point is present on this curve, then we need only one variable. Okay, if any point is there, so you need only one variable, then with that we can correspond with that, only another variable. Only one variable if you get, then we explain that about of these points if it is present on the curve. Similarly, if it is present on this area, then for that we need 2 variables, one for temperature, other for this pressure. Okay, and if the point is present on this curves, then we it not need any variable, because this is the fixed value if the point is present at triple point. Okay, and one more we will discuss about one component system, that is solve for, because sulfur, it exists in 4 phases. Like it says this is solids, and if it says that liquid, and if it says that vapor. But these solids exist in 2 forms. One is rhombic sulfur and another is monoclinic sulfur. That I can say SR, I can say this is SM, this is SL, this is SB. Then what these 4 pages we will get, because whenever a components, whenever we say that as what I say that A solids plus B solids plus C liquids plus D gas, then how many pages are there? So each solids will give different pages. So this is 2 plus liquid for 1 plus gas 1. So 4 pages are there. So what will be the page diagram for this sulfur? Okay, so since this also again slope is positive, so we will draw this way. Okay, so how will the page diagram? So I can write the pressure by temperature, so positive slopes. So this is the positive slope I can draw, and what I do is okay, so here what it says that this below area, let's say this is A, let's say O, B, C, D, E. Okay, so let's say this below area is vapor area, so let's say SB or vapor area. Okay, and this area is liquid area, and this solid area is divided by 2, that is one is for rhombus and the other is for monoclinic. So let's say this is for monoclinic and this is for rhombus. Okay, so now what I says that we will discuss 3 things. One is for curves, another is for areas, another for triple points. So we will discuss these 3 things. Okay, so let's discuss about of the curves. So curves is, this is AO. AO is also present. So in this AO, what things are there? In the above, what is there? Rhombic, and below sulfur, so they are in equilibrium. So in AO curves, rhombic and vapor is in equilibrium. Similarly for curve, let's say OB. So in OB, what are the above side monoclinic and downside is vapor, so I can write SM and SB. Similarly for BC, curve BC, that is above side liquids and downside is vapor, so I write S like vapor. Okay, similarly I discuss this. So this ODB curve, DB, what is that? Curve DB, what is that? One side SM, another is SL. So SM and SL, liquid and monoclinic in equilibrium. And similarly I like DO, so one side rhombic, another is monoclinic, so I write monoclinic and rhombic. Similarly this DE, this curve DE, one side is this liquids, another is rhombic, so S liquids by S rhombic. So same case like here, all in the curves, what page is See here, suppose let me discuss for curve AO. So same things applicable for curve DP, curve DO, curve D, all these curves same. So let's discuss one. Curve AO. So how many pages? 2, this and this, and components is 1 because you're discussing one component systems, although you can also take that 2 species is present and one condition, so component is 1, and degrees of freedom means S minus P plus 2, so C is 1, P is minus 2 plus 2, that is equal to 1. So if any points, if it is present in these curves here, suppose x, so to explain this we need only one variable. So if we point it out, then this has to be this, so only one point is needed. Okay, so similarly curve areas will say areas, let's say this A O B C. Okay, this area A O B C, here, here, here. So here only vapor is there, so A O B C. Okay, this total area A O B C, this total area only vapor is there. So similarly if we says let's say that area of CBDE, area CBDE, only liquid. Similarly this area of EDOA only rhombic surface. Similarly DOB only monoclinic. So if any point is present here in this area, then how many curves are needed, how many variables are needed? So in this way, how many pages? Let's say for area CB, okay, I will discuss this. Let's say any area, let's say AODE, area AODE. So for this area, if any point is present here, then how many curves we need? So AODE, only one page is there. Where is AODE? Only rhombic, so page is 1, and since we are discussing one component, also no condition is there, so component is 1, so F equal to C minus P plus 2, so page and C is 1 1. Sorry, so this is 1, this is 1, 1 minus 1 plus 2, this is cancelled, that's 2. So if any points, if it is present on this area or any area, then we need the two variables, one for this pressure, another is for temperature. So two variables are needed. Okay, because F is equal to. Similar case we can explain, we can find for all areas, where also whenever you calculate this F, we will get 2, means two variables are needed. And for triple points, here the triple points is another, this is the all these curves or stable curves, this is stable curves. Okay, and we also present metastable curve also. Let me discuss metastable curve also. So this area, if you extend this one to here, or I will draw in some other, this one, okay. So if you extend this curves to here, then this will go to here, and if it will extend to this value, then this is extend to this here, and if you extend to this curve, then this will go here, and if you extend this, then this is go here. Let's say starts in this point, and it will extend this, then it will come to here. So this is another point. Let's say L. Okay. So this point, this is the triple point, but this is metastable triple point. Okay, and this extended, whenever I extend this OB curve, then this extend board. So let's say this is BH, and let's say O, let's say OT, let's say, and whenever, okay, so this much. So here, but things also need that the previously I draw the stable curves. Now I draw the curves that is metastable curves. Metastable curves. What are metastable curves? These are metastable curves. This. So whenever extended this OB, okay, so BH, curve BH, okay, so this curve BH, whenever I extend this curves to here, then in this curve, whatever you see, whenever I extend this curves, so here BH, so this BH extended from here, so whatever will get that equilibrium, the same things will be get here. So this OB curve is equilibrium of SB and SM, so this is also SM, B by SM. Similarly, this one I extended from here, yes, so this extended to comes here. So whenever I says curve OT, so this extended from here, so this is the same as this. This is again SB by SM. Okay, because these curves I get whenever I extend this. So this BH is not equal to let's say this is SL by SB, not, because this curve I get by extending this one. So this curve BH is by SB by SM. This is right. And if you simply look it, then BH should be, one side is liquids, okay, another is SM. Then it may be, you may think that SL equilibrium with SM, because one side is liquids, another is SM according to this, but this is wrong, because this curve comes after extending this OB. So whatever this OB equilibrium is there, same will be comes from BH also. So BH is SB by SM. Similarly for OT, curve OT, this curves comes whenever we extend this, whenever we extend this OB, so OT also, that will be SB by SM. Okay. So similarly, another curves, this this point is SL. So curve what OL. So this OL, which comes whenever we extend this AO. So whatever this AO equilibrium is, one side is SR by SB, so this is same as SR equilibrium by SB. If you simply look that what OL should be, because this is monoclinic and this is SR or SB, you may think that this is SM should be equal to SB, because this is here, so one side is this, other side is this, may accommodate, but this is wrong, because this curve comes after extending of this one. So whatever the equilibrium this AO exists, the same equilibrium exists by OL. Similarly, this curve BL, that is BL, this comes whenever we extend this BC. So BC is equilibrium with SL and SB, so this also comes to be SL by SB. Okay, so same that if you calculated that page also comes to be 2 and components is comes to 1, and whenever you calculate that F, then also it come is 1. So same as like curve, same they will calculate. So you can calculate it, the same value will get. Similarly, the triple points here, so triple points are one is this O, another is this B. Triple points are O and B. So this O here, one side is SR and here is SB, another is SM. So triple point O, that is exist in one side is SB and one side is SR and other side is SM. Similarly, triple point B, what one side SL and below side SB and inside is SM. And metastable triple point, this is L. So metastable triple points, and this is let's say this SL, what sorry so metastable point L, a metastable triple point L, this L, this L, so this points is comes from here. One is this curves comes because of this, and this curves comes because of this, and this curves comes because of this. So for this curves, so this this curves comes from because of this. So this is equilibrium with. So if it says that this curve, this point L, yes, this L is comes from here, and this curve is comes from this curve is comes because of this. So this is let's say SB, and this curve comes because of this. So let's say this is SL, and this curves comes because of this. Let me write. So this curve, I write in another page. So this curve comes because of this. So these curves I can write, let's say SR, and this curves comes because of this, let's say SL, and this curves because of comes here, so let's say SB. So this metastable triple point is SR, SL, SB, not SM, because this curves comes from here. So this curves because of this curve because of this curve because of this. So this is SB, and this is SR, this case is SL. So SM is not there. So this metastable triple point L is SR, SL and SB, not SM will not come. Okay, so at this point also, if you calculate C and P and if you calculate F, you will get 0. For explaining this metastable triple point, we will not need any variables. Okay, so like this we will find that if any point is present either at on area or on curves on at metastable points, then what are the variables we needed? For that we calculate the F, and it F is comes 0, then it is fixed, we not need any variables. If F comes 1, then we need 1 variables. If F comes 2, then we need 2 variables. Okay, so today after this, thank you.